Hey everybody, welcome to ElectroLisa. In today's episode, we're going to look at this ZX Spectrum Plus. It came to me with an issue with the output display where it was showing something that was definitely not what Sinclair intended for the machine. Now, a garbage display in this machine could be a lot of things. The most common one is the RAM. However, in this specific case, after some methodical tracing with the oscilloscope, I found out that the culprit was the ULA, the glue logic custom chip that every ZX Spectrum has. It couldn't drive properly one of its data lines, and that was corrupting everything downstream. Now, I will also show you exactly how I got there, and I'll show you how I fixed it. I did so not using an old second-hand ULA chip, but with a modern drop-in replacement that, besides fixing the display problem and replacing the chip, also adds the RGB output capability to the machine and also the AY sound chip. And all of this doesn't require any soldering at all. So let's get started. Now, before we open this machine up, I want to give you a little context on where it comes from, because the Spectrum doesn't exist in isolation. It's the product of a very specific design philosophy that Sir Clive Sinclair pursued across for almost a decade. And understanding that lineage makes the machine's architecture a lot less surprising. It all started with the ZX80, which was launched in January 1980 at a price of £79.95 in a kit form, and then £99.95 in fully assembled form. The first computer that was actually available in the UK below the £100 price tag. It used the Xerox processor Z80A, clocked at 3.25 MHz. It had a 1 kilobyte, that's a K, of RAM and 4 kilobytes of ROM. The defining constraint of the machine was that it could only generate a video signal while it was not executing code. So the moment the processor was busy, the screen blanked. At that moment, it was actually losing synchronization. So the engineering of Sinclair was very radical cost reduction taken to its logical extreme. Now, a year later came the ZX81. It sported the same Z80A processor, the same 1K of RAM, but now it had a proper ULA chip, which handled the video generation independently. So that it did eliminate the screen blanking of ZX80. The membrane keyboard was famously horrible, but the machine sold over 1.5 million copies, and it was expandable to 16 kilobytes via the RAM pack, which had an equally famous habit of wobbling and crashing the machine at the worst possible moment, of course. I have a broken ZX81 on the bench waiting for a future video, so we'll definitely come back to this one. Now, 1992 brought the machine we're working on today, or rather its direct ancestor, which is the original ZX Spectrum. It launched in two variants, which was 16 and 48K of RAM. The processor stepped up the Z80A to 3.5 MHz, and it had a color display of 256 times 192 pixels with 15 colors. It was a genuine leap over the ZX81's monochrome output. So the 16K variant was particularly relevant in the video that we're making today, since it could function, so any ZX Spectrum can function with only with 16K of RAM, which helps us a little bit here. But we'll come back to this later. Now the 48K variant launched alongside the 16K at £175, and it became the machine that defined a generation of British computing. So extra RAM opened up software that simply wasn't possible on 1 or 16K, and huge games library that followed as well. And this is the machine that we're working with today. So specifically, that's the Plus variant that came in 1984. It did keep the 48K internals, but the rubber keyboard was finally replaced with a proper one, let's say, and a reset key. Now, the board inside is issue 3B, the most common 48K revision that existed. Now, what happened later? In 1985, Sinclair expanded the architecture substantially with the model called 128K. Well, it was actually called Toast Track because it did have a very specific case. It did develop this machine, so Sinclair did develop this machine for the Spanish market initially with in a partnership with a company called Investronica. It did add 128K of RAM. It used bank switching to access it, of course, since Z80 is a 16-bit, 8-bit processor, 16-bit address line. Now, it also had a 3-channel AY38912 sound chip that replaced the single-bit beeper. That's an extension that will be installing in this machine too. And it also had an RS-232 interface. There were also 122K variants that were produced later, including the Plus 2 and Plus 3 machines that were made by Amstrad after they acquired Sinclair in 1986. And they did extend this platform's life significantly into the late 1980s. Now, I would also like to mention the last original design from Sinclair, which was called QL, or Quantum Leap. It was launched in 1984 as a professional machine aimed at business users, built around the Motorola 68008 processor running at 7.5 MHz. It had a 128K of RAM. It was technically ambitious and commercially troubled. So it was plagued by delays. It shipped with a ROM that required external dongle to fix bugs eventually. Then it was ultimately overtaken by IBM PC and the Macintosh. However, it is a fascinating machine, and I hope that it will make its way one day onto my bench and into my collection so that I can play with it a little bit. If you want to take a look at Sinclair QL, there is a very nice video by Dan Woods on his channel that you can look at and see what the machine was all about. Now, QL marks the end of the Sinclair line that we follow today. So the line started with ZX80, came through ZX81, the Spectrum 16K, 48K, and the variants of 128K, finishing with the QL. However, what connects all these machines is Sir Clive Sinclair's consistent conviction that computing should be accessible. It should be cheaper, simpler, and in as many hands as possible. And the architecture of every one of these machines reflects that conviction, sometimes elegantly and sometimes in ways that created interesting problems, like the one we're going to see today. Let's take a short look into how I got to own this machine. So my first personal computer was a Commodore C64. It was bought in the early 1990s. I think it was 1990. The availability of even the 8-bit micros here in Poland was pretty limited back then. So once the communist government collapsed, we got some hardware flowing, usually from the West Germany. And that was the way I got mine. It was, I think, the C64G version. Now, I was reading a lot about other types of hardware, including ZX Spectrum, because in the 1980s we didn't have too much access to those, but definitely I was curious and I wanted to understand what these machines are. So I read every book, every magazine that I could find to get familiar with those machines, and I coveted having some computer in the middle of the 1980s as well. Now, we did have a computer called Elvro 800 Junior here in Poland. It wasn't accessible anyway, but it was mostly bought for schools and it was essentially a ZX Spectrum clone. I don't really think that Circlife approved nor knew, not so certain about that, but regardless, it was mostly compatible with the original, but it was a bit extended, meaning it had a mechanical keyboard. It had an optional external disk drive. I think it was 5.25 inch, not the 3-inch jobby that Amstrad later added. And interestingly, it had also the ability to network with other Junior machines. It had a network called JUNet, which connected a daisy chain of machines in a ring. It allowed for classrooms to do stuff in unison. I was able to finally get my hands on one of those. I didn't even power it on. It's just sitting in my storage. I just bought it last week. But of course, we will definitely take a look at it at its own due time, a couple of months. And we'll try to see. I hope it's broken. I do assume, given the price, those units are pretty pricey right now. So I assume it's going to be broken, but let's see. Back then, back in the early 90s, my school had a few of those. I would say we didn't use them that productively. Mostly they were breaking a lot. That was the first thing. So we had like a huge heap of those Elvro machines lying there in the corner of the classroom. And we also used to play with the ones that were working, kind of exchanging the keycaps all over the thing or putting them upside down and stuff like this. But mostly pranks, but nobody wanted to work with it. So we had like a 1 or 2 MSX machines, which we used, and also some early PCs like the XTs and 80s, the 286. So right now, like 1 or 2 years ago, when I came across this specific machine on an auction, it was in pretty good condition and reasonable price. I bought it without any hesitation because I wanted to get my hands on a Spectrum and see how it works and what it does. It was a good call because I actually learned a lot about the machine itself, and also how, regardless of the poor graphics nor the capabilities, which were somehow limited compared to the other micros as well, that you really can have fun with it. So I'm really curious into taking it to the next step, learning some assembly and so on. Now, when I fired it up the first time, it was pretty much working. I knew it had the composite mode done because you could use the same cable we are using throughout this video until the last moment of it. So it doesn't need to work on the TV channel. It's already outputting the composite video signal. However, the keyboard wasn't working at all. So I had to, first of all, to replace the membrane. So the machine was showing the Sinclair logo and it booted. But after a couple of runs, it actually started to develop the video output like we are seeing in this video. And ever since, it hasn't turned on. So before diving into the work on diagnosing it properly and the display fault, I kind of future-proofed it a little bit. So I did replace all the capacitors on the board with proper ones. It had already new capacitors, but they weren't radial, and I kind of wanted the mainboard to look pretty original, let's say. I did buy and replace the keyboard membrane as well. And last but not least, I made sure to replace the 7805 voltage regulator. That's the silicon that converts the 9 volts DC that the machine is getting to the 5 volts that it needs. However, in the process of doing so, linear regulators produce a lot of heat. That's why it needed this extensive heatsink, which it originally had over the board itself. But it was very inconvenient to work on the machine with that heatsink in the way, especially on measuring the CPU and the data lines and so on. So I decided to change it with a device like a switching regulator, which was called Traco Power TSR1 2450. It does convert the voltage to the 5 volts, but it's a modern replacement of the 7805, It does introduce a little noise, but I did some measurements with the oscilloscope, and the difference between the 7805 and the track power is pretty minimal. There are other alternatives on the market which in some videos people claim that are less noisy, even less noisy than the track power, but I did buy those and I tested those, but track power was simply the best for it, so I ended up with that. It can run up to 1 amp of current through this switching regulator. It's good enough. I checked the power use of the machine, both just running idle and also with the additional interface, the Just Nano SD interface that I will install in the last part of this video. And it's just maybe a little bit more than 200 milliamps of power that we're using. So it's well below what the switching regulator can run. I really recommend this as a change. Now, once the BASIC was sorted out, what remained was the display problem. And since I didn't have anything to lose and it wasn't working anyway, that was a perfect opportunity to understand how the ZX Spectrum works. So that's when I started to diagnose and work on it. Now bear with me for a couple more minutes, because before we will start to work on the ZX Spectrum itself, I want us to take a look at the power supply. And I cannot overstate how important it is to check the power supply before you start working on the machine. So I actually did learn it the hard way. I did spend quite a significant time tracking problems with my C128. I ended up replacing the capacitors in the machine, the video chip. I ripped a couple of parts doing that, and that's another video that we need to make to actually fix that machine after what I did to it. But long story short, eventually that ended up to be just the power supply, and it was just badly regulated, causing the machine to not function properly. So the power supply must be checked first before you actually start doing anything with the machine. If you have an uncertain power supply, make sure to verify. All right, so what we have here is the ZX power supply, the original supply that came with the machine. From the label here, you can read that it's 240 volts AC, 50 Hertz, and it outputs 9 volts DC at 1.2 amps. Now, before we do measure it, there is one important thing that we need to know about the Spectrum's power connector. It uses reverse polarity compared to what you usually get on the market. The positive terminal is on the outside of the barrel jack, and the negative is on the inside. Usually it's the other way around. So make sure you verify that whatever you're using uses the same approach, because otherwise you might damage your machine. Now let's measure this supply. So let's connect it first. And then we take a regular multimeter, set it into voltage mode, and then again the positive terminal goes to the outside, the negative to the inside. There is no switch, so it's already on. What we're getting is 14.46 volts. It is a little bit high. Bear in mind that this is not a regulated supply. So the idea is that without a load, it will have a bigger output voltage than when proper load is connected to it. However, I do know that 14.5 is a little bit high for those. It should be something around 13.5, but might also be related to the input voltage and so on. However, I cannot test it properly under load because I don't have a proper electronic load in here. So without doing that, I am totally not certain if it is safe to use it on the machine. So we'll put it aside. We'll not discard it. We can take care of it later. However, for now, we'll use something else. So let's disconnect it and put it aside. And what we'll use instead is this compact plug-in AC/DC adapter. Its model is XBS-0920. The input is AC 100 to 240 volts out at 50-60 Hz. Output is 9 volts at 2 amps. So it's more than original supply could deliver current-wise. And it has some slack space for any additional devices that we can connect to our machine. Again, look at the polarity diagram here. The plus is on the outside, clearly marked, and the negative is on the inside. Let's connect it and measure. But before we do so, there is one more thing that I'd like you to notice on this supply. What it also has is an inline switch on the DC side of it. And that is way more useful than it sounds, because ZX Spectrum doesn't have any power switch at all. So what you do is you tend to switch it on and off by just putting the power connector in or out. The problem is that the DC connector on the main board tends to wear over time, and it can lead to issues. So it's very, very convenient that we have this switch with which you can switch the computer on and off. In this case, to measure, we'll switch it on. And again, positive on the outside. Negative is a bit more difficult because we need to match one of these two pins inside. It's not round, but we see a perfect output voltage of 8.95 volts. This is exactly what we expected. Right, now that the power supply is verified, we can open up the machine. Now let's take a look what happens when we power the machine on. We can see like a test pattern in the beginning, which is quickly replaced by these vertical tabs, but there is some activity ongoing. So the expectation from me at least is that the Z80 CPU is actually trying to do something. We have the ULA, which is not super hot yet. One more thing that we can do before we try probing on the board is we can try to run a test cartridge. It's called a diagram. This is what I have. So this cartridge has 4 possible ROMs. It has Gosh Wonderful, ZX Diagnostics, RetroLeum diagram, and ZX Test diagram. We'll run the RetroLeum one, which I know more or less. Power is off. Always. Power has to be always off, remember. Alright. Let's push it on. Let's run the machine. Alright. So this is a very important symptom, because what you can see is that there is a test ongoing. The test is running. So that means that the CPU is actually executing something. And now it's showing that it did detect bad RAM, if I'm not mistaken. But the fun thing is that it's actually doing something, which means that the CPU can execute code. All right, so we have our first symptom and our first diagnosis. So now that we found this, we need to probe the RAM. First of all, we need to take care of the voltages. So we need to make sure that every chip on this motherboard is getting the proper power for it to function. As we saw on the screen, the code is being executed, so I'm not really worried about the CPU not getting proper power, but we'll check that too. But what we see, this is the schematics of the ZX Spectrum issue 3B. What we can see here is that we have the ULA, we have the lower RAM memory, which is the most suspected culprit at the moment, which needs plus 5 volts, plus 12 volts, and minus 5 volts. Then, of course, the ground. And these are all the 4 voltages that it needs. Then we have the upper memory, which in turn uses the plus 5 volts. But in this case, we don't really focus on this that much because the upper memory seems to be working correctly. We also have the ROM, which is right next to the CPU on the motherboard, and a couple of glue logic used to multiplex the lines. So when we take a look at the layout on the board, we can see that, if you compare it to the board itself, we can see that IC2 is the CPU. There we have the ROM. This is the ULA. This is the lower RAM chips. And this is the higher RAM chips. These are capacitors. As you can see on the mainboard, I actually did replace all of them with the proper radial capacitors, because the machine, when it came to me, it was recapped, but it was recapped by a regular capacitors just sitting vertically on it. So first of all, let's take a look at the RAM. Each of those 8 chips is responsible for 1 bit of a complete 16K of memory. So it means that we have, each chip has 16K of 1 bit memory, and then they together form 16 kilobytes. Each byte is 8 bits. But every byte in the machine's memory is comprised of 1 bit from each of those RAM chips. What we can do right now is, let's take a look at the power at the RAM chips. So again, we'll set up our digital multimeter in DC voltage, and before we probe, we need to take a look on the chips themselves. Pin 1 is right next to this little marking on each chip, not the dots. These are my verification of those chips, and I marked them, but actually there is like a little bit of marking here as well on every chip, which signifies the part with pin 1. So the ground was VSS. VSS is on pin 16, so it's always here. And pin 1 will be VBB, so minus 5 volts we should be getting on pin 1. So the machine is running now, and here we should be getting minus 5. It's minus 491. Let's check the others. It's the same. It's also the same. 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 And same. So we know that the minus 5 volt is working correctly. Now let's check the VDD. So plus 12. It's pin 8. So this pin here. All right, it's 11.90. It's perfect. Close enough. Same. Okay, the machine is rebooting. We don't care about that as long as it's operating. Okay. 12. 12. Same. And the same. All right, and the last voltage that we want to check is the plus 5 volts. So we'll do a little bit of switcheroo on hands. I'll connect the ground to this pin, and we need plus 5 volt on each one of those. Okay, it's 4.92. 4.92. Sorry, my ground is a little bit shaky. Let's connect to this. 491. 491, 492, same, same, and the same. Okay, so the voltages on the RAM are correct. Now let's take a look at, sorry for the beeps, at the CPU. What we see on the CPU is, this is kind of a big printout of the pinout of the CPU. It should also have some power pin, and here we got it. It's pin 11. And then we need a ground pin, so it can be pin, say, 29, right? So let's find pin 11 first. It should be the positive 5 volts. So let's count from pin 1. Pin 1 will be the one closest to the notch here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Cool. So we're stuck on pin 11. Then pin 29 is 21 starts here. So it's 21, 2, 3, 4, 5, 6, 7, 8, 9. That should be 29. Okay, we're getting 488. It's perfect. Now, the last thing to check is the ULA power. So again, plus 5 volts should be there on pins 13 and 14, while the ground is, for example, on pin 40. Makes it easy. So again, pin 1 is here. The ground we connect to pin 40. And we need pin 13. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, interesting. We have 3.6 volts only. And 14. We have proper power on this. Okay, that's interesting. Let's first check whether the 3.65 volts that we saw on the VCC2 of the ULA chip could become a problem or not. So what we're looking at here is the schematic for the ZX Spectrum issue 3B specifically, so the one we're looking at on the bench. Now let's take a look at the ULA itself. It's this chip here. We need only to focus on a small subpart of this circuit, so let's do that first. So we saw VCC1 being at close to plus 5 volts, which we expected. And when you look at the schematics, it's pretty obvious that that's what we should be getting, right? So we're getting plus 5 volts. Then we have like two capacitors, which are just used for filtering / decoupling of the signal to the device. So it shouldn't be a problem with the capacitors undamaged. That should be close to plus 5 volts. Now VCC2, the one we saw lower voltage at, it's a bit more complex. So we have this set of capacitors and a resistor, which also probably are busy with filtering this signal and removing some noise on this. What's interesting is the big power of this resistor, so it means that the power could be substantial that is going through this line. Now the actual voltage comes through this line, so let's trace it back. We go here and we see LK3, that's link 3. It's just a dead short on the main board, meaning like it allows for some configuration. In this case it's connected. Now this connection goes to two places. One is the pin 3 of the LM1889, which is the video generation chip on the main board. So it takes the signal from the ULA and transforms it into something that our monitor could actually display. Now this signal is also decoupled to the ground through a 47 nanofarads capacitor, and it goes through a 470 ohms resistor to plus 5 volts. We would expect some voltage drop here in the first place, but there's also this set of transistors here which go to the V line on the ULA. That can also affect the voltage on the chroma bias pin. Now, whether this is a problem or not, I'm not really certain. I'm not super great on the analog circuits and I'm only learning how to understand those now. So for now, I would assume and take the hypothesis that the chroma bias signal could be something different than plus 5 volt. And then what we're seeing on pin 13 of the ULA is expected, meaning it's not the biggest fault on the board. Having said that, if somebody knows what the difference is between VCC1 and VCC2 on the ULA, please tell it in the comments below this video. I'm really curious. I couldn't find it through like a quick search online. I will still browse through the Spectrum ULA book that I didn't fully read yet. But in the meantime, let's focus on the data pins of those chips and see whether they are okay or not. So let's do some diagnostics. What I did off screen is I configured my Rigol so that we can also save the traces onto the pen drive, so I can show you those in more detail. Now we'll start with the 4116 RAM, and we'll go through first the data in and out for each of the lower 16K RAM chips. Now those pins, they represent 1 bit of the entire RAM. So each chip is the whole 16K, but just 1 bit of it. So bit 0 is in one chip, bit 1 is in another, and so on. So we have 1, 2, 3, 4, 5, 6, 7, 8 chips here on the board, which means that builds our entire 8 bits per byte. Now, what we're interested in is we'll look into the data in and data out pins, so whether the activity on the data lines is correct. But then we'll also look on the address pins, so whether the chips and the activity generally on the address bus are correct. So let's do that. So the oscilloscope is set to 1 volt per division. We have -2 volts set as the baseline, so the vertical is down by 2 volts. So we would see 1, 2, 3, 4, 5 volts exactly here. What's important is that the probe, the Rigol probe, it's not very great, but it is what it is set to ×10, and it's the same in the settings of the channel of the oscilloscope. So you can see that the probe is set to 10 times. But what's important here is that it's showing less noise on the changes of the signal given the high frequency of those, right? So when we're measuring such high frequency data lines, it's better to use the probes at ×10 setting instead of ×1. Although it wouldn't mind, like the voltage levels are still okay. Now what I did as well is I connected the ground to the ground pin on the reset switch, which is convenient because we can move it a little bit around. It can add some additional noise. Actually, let's cut it out, and now I will actually repopulate the switch. So, and we'll just check whether this capacitor has also a ground connection. It does, so this is the ground as well. It will be closer to the chips, so let's do that. We will have less noise. And I'm also worried that we might get some additional issues when the cable could be moved back and forth. So let's start the machine. Now, again, we know from the datasheet, you can take any datasheet of 4116, they are compatible. Sorry for the noise of the machine. That's the tests, the retro-leum test running, round and round. Now let's start with the data pin. So data in is pin 2. So let's connect. Be very careful, by the way, not to short the nearby pins, because you can get rid of your RAM that way. Now let's connect to pin 2. As you can see, what we'll have, we can also play a little with the time base of the signal. We have some activity. Doesn't look especially healthy. We can play around with the trigger level a little bit. You can see that there are different types of signals that are over each other. My suspicion is that in this specific case, this is the ULA communicating with RAM and the CPU communicated with RAM. Both do it in a little bit different way. Therefore, we're getting this kind of strange noise. But as you can see, there is activity there. Let's save this. And let's also check the other RAM chips. So do we have activity on every one of those? We have on the second one. We do on the third. We have the same thing on the fourth. Same on the fifth. Same on the sixth. Same on the seventh. And the same on the eighth. So we're good. Data in is fine. Now let's take a look at data out. So it's chip for pin 14. So we count, this is pin 16, since this is a 16 pin chip. So it's 16, 15 and 14. Okay, let's save it. Takes a while. All right, so it's fine, by the way. And let's check the other chips. So data out is also well, so we see that reading the chips is also something that is happening, meaning the computer is actually doing it, and there is activity there, right? Okay, now let's go to the data line. So first we'll go bit by bit. We'll start with A0, which is on pin 5. So let's do that. It's 1, 2, 3, 4, and 5. All right. As you can see, we see also activity here. Let's save it. By the way, you don't see people writing stuff down so much in some of the films on the internet. Believe me, that's what they're doing anyway, meaning everybody has to take a lot of notes, document whatever they are doing, and so on. Like, without that, you're basically screwed. All right, let's go through pin 5 on every one of those. 1, 2, 3, 4, 5. It should be the same, but of course we have to eliminate the issue where one of those memory chips would be not connected properly. So chip 2 is fine. 1, 2, 3, 4, 5. Chip 3 is also fine. Chip 4 is also fine. Chip 5 is also fine. 6th also fine. 7th is fine. And 8th, it's fine. All right. Address line 1 is pin 7. 1, 2, 3, 4, 5, 6. Okay, it's 1 from the bottom. Ooh, okay. Let's take a look. Address 1 line. Let's lower. Something is happening there, but it's definitely not what we expect. Let's save it. Okay, saved. Let's check if it's happening on every pin. Yes. 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 And yes. All right. Data 1 line is very suspicious line. Now let's go to data line 2. Let's test all of them. Let's see if that's the only one. So it's pin 6. 1, 2, 3, 4, 5, 6. This one looks fine. Okay, let's wait for the saving. All right. Oops. Same. 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 Address line 2 is fine. Keep mixing those up. Now let's take at number 3. So it's fourth pin down from the bottom, and it's A3. So it's 1, 2, 3, 4. Okay, we have activity. Save it. Fine. And let's check the others. Okay. Okay. Address line 3 is fine. Address line 4 is the third from the bottom. Looks fine to me. Save it. All right. And let's check the others. Fine. Fine. It's fine. It's also fine. 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 Perfect. Address line 4 is fine. Then address line 5, so it's pin 10. It's the second from the bottom. It's looks good. Save it. Now here we're close to VCC. VCC is fine, by the way, but some of the voltages can be really dangerous. So again, watch where you're adding your prop. We're checking the remainder of the memories. You might think that all of them are connected to the same address bus. So why am I checking? They're fine. By the way, why am I checking all of them? Let's check address 6. So it's 13 is the fourth from the top. 1, 2, 3, 4. Okay, save it. I am checking those because in this old machine, as you can see, all these chips are seated in proper sockets, and those could not make proper contact. That's the problem with it. All right, let's continue. So it's fine, by the way, and the remainder is fine. It could not make contact to one of the memory chips and prevent it from operating correctly. Oh, sorry. I thought we had something, but not really. I was the one not making contact. All right, so we checked from A0 to A6. Do remember that these chips are only 16K, not the full 64. So we only need 7 bits to address those. We don't need the full 8. So there isn't an A7 line here. So what we verified so far is that the RAM chips are operating correctly. However, we see that the address line 1 is not really signaling properly. So not the whole signal is working correctly. That would explain what we see on the screen. So the memory addressing is crappy. But we do see that the CPU is operating. So that's a clue that only the display is affected and the CPU is able to run. Of course, the RetroLeum can be reading from its own ROM only. So if there was some code stored in the memory, it could also be garbled. But in this case, we know that the CPU is able to address the ROM and work with it. One important design choice that the Sinclair engineers made is that the lines between those two chips, so the CPU and the ULA, are separated from each other through a set of resistors on the data line. So, or I think address, I need to check that. But long story short, whoa, the ULA is hot. Okay, now that we're done with RAM, let's take a look at the Z80 CPU. Now, as you can see, we have way more address lines. We would need 16 because the addressable space, the addressable memory of the Z80 is 64K. And in order to have that, we'll need to have the full 16 bits of the address line. Now, by the way, regarding the RAM, that address lines are multiplexed, right? So we don't really need so many. But going back to the CPU, what we'll check is all the data lines that it has. It will be 8 because that's an 8-bit CPU, right? So it operates on the 8-bit words basically when it sends something on the bus. Now, so let's start with the data lines and then we'll go to the address lines. So let me make a note. So it will be CPU, and we'll start with D0, which is pin 14, then D1, which is pin 15, then D2, which is 12, then D3, which is 8, then D4, which is 7, D5, which is 9, D6, 10, D7, 13, and that's it. All right, so let's take a look at those pins. Again, let's switch it off. Let's find a ground pin that is close to the CPU, so it can help us making all these measurements. Okay, the ones here are fine. So those two pins on the capacitors. Let's switch the clip of the oscilloscope here. All right, we're ready. Again, probe is set up fine. Machine is running. Now let's see. Data line 0 is pin 14. So this is 20, 19, 18, 17, 16, 15, 14. Perfect. We have some activity. Let's save it. Okay. Now data line 1 is 15. So it's 20, 19, 18, 17, 16, 15. By the way, I'm doing it manually, so to say, meaning counting those all the time because I just want to be sure. Okay, we're saving data line 1. Now 2 is 12. So it's 20, 19, 18, 17, 16, 15, 14, 13, and 12. Get activity. Save it. Okay. Now 3, which is pin 8. So it's 1, 2, 3, 4, 5, 6, 7, and 8. That's D3. Save it. Now D4, which is just one above. Activity there. Save it. Now we're looking for D5, which is pin 9. So it's here. Perfect. There is some activity there. Again, saving it. D6 will find right down by one pin on pin 10. Let's connect to it. Again, there's activity. As you can see, our measurement isn't really affecting the execution of the code from the ElectroLisa test ROM, which means the CPU is still running perfectly well. Okay, we're at D6 and we'll look for D7, which is 13. So it's 20, 19, 18, 17, 16, 15, 14, 13. Perfect. So all the data pins seem to be working fine. One thing that we'll want to check on the CPU is also the clock. We see the computer operating, so I really do not expect any issues with it, but let's measure it. So the clock is on pin 6. So let's find it. 1, 2, 3, 4, 5, 6. Let's measure. We have a perfect 3.5 megahertz, what we expected. So let's run with the address lines on the CPU. So address 10 is actually 0 through 10 are located starting with pin 30 on the right side of the CPU, and they'll go up to address line 10 at pin 40. There are cats fighting around the house. Nice. I don't know if you can hear it, but that's interesting. or sounds like children crying in some complicated melody. But anyway, we're looking for pin 30. So let's find it. It's 40, 39, 38, 37, 36, 35, 34, 33, 32, 31, 30. All right. The rest lines, they look a little bit different. They actually look cleaner. I like it. So that's address line 0. Looks okay. Save it. There's a real war going on. Now address line 1 looks good. Save it. You can see the address line changing when the execution is happening. That shows us healthy execution. Address line 2, it's fine. So as you could see on the lower RAM, we had addressing issues on pin 1 or pin 2. I'll check in with the notes. But long story short, we cannot see them here. That's interesting. Okay, next one. Okay, let's save it. Looks fine to me. Next. Looks good. Save it. Wow, there's like real war going on out there. I don't know, guys, if you can hear it, but it sounds great. Okay, next pin, same thing, addressing. CPU is addressing as intended. All right. Next, again. By the way, you can see the changing pattern, but that's like an addressing change for the code execution again, so do not worry about that. So we're at, it's 1, 2, 3, 4, 5th from the top, 1, 2, 3, 4, 5th. So it's address line 6, now address line 7. Looks fine to me. Okay, that's some nice activity on address line 7. Address line 8. Nice, it's working. It is a bit messy here, to be honest, like the levels are changing a little bit. And still there is activity. Address line 9. Again, looks similar. And address line 10. Okay. Save it. Again, the higher we go, the bigger the changes that are happening. So, of course, the higher bits on the address line, they change the groups of RAM. So at some point, we'll have the bits that are responsible for the lower versus upper memory within the addressable space and so on. So the changing of them will be different, and the lower bits are working more than the higher bits, so to say. Okay, we were at 10. The 11 starts at pin 1 and goes down to pin 5. Okay, so let's do just that. Pin 1, stuff is happening. Let's save it. As you could see, it was 0, it was flat for some time, but that's again because the bit was not really being set by the CPU. We're doing fine. Now pin 2, again, similar activity, A12. A13, again. Okay, could see it changed. Now it's changing again, so this bit is being set and reset. Okay, A14, again. And finally A15, similar thing. All right, but basically what we can see is that none of the address lines and nor any of the data lines are affected on the CPU. So CPU is able to operate correctly, it's able to read ROMs correctly, and it can operate. So, and that's what the video is showing as well, the output of the machine. So now tracing back to what else is actually interacting with the memory to show us the picture, we naturally get to the ULA. So again, let's switch the machine off. Let's find a proper ground source for us. This is described as plus, so this should be here. It is. All right. Let's connect the probe to the negative pin near the ULA. Again, the closer you are to the chip, the better quality of signal you will get through the probe. This is the default Rigel probe that I got with the oscilloscope, so it's not the greatest, but it will do for our purposes. So let's switch the machine on again. Now we're looking through the ULA pins, but first of all, let me show you the diagram of the ULA. What we see is basically these are the two voltage pins, the voltage supply or power supply pins. This is ground. What we have of interest here is pin 32, the clock, which will check the first. Then we'll get through the data pins. They are distributed, so data pin 0 is here, 1, 2, and so on, but we'll go through them. And then once we're done, we'll go through the address lines. As you can see, you have the same 7 bits of addressable space from the ULA as we had on the lower RAM chip, so address line 0 to 6. So ULA is directly communicating with the selected subset of the memory, which is not really the case when the CPU is accessing those. It has the full 16-bit addressing space, and again, there is a conversion that is happening between the CPU and the lower RAM, where there are some chips here, the kind of regular 70 LS logic chips, that do as multiplexing units for accessing the lower RAM from the CPU. So with that in mind, when we're looking just as the subsystem of the video generation, which is kind of trending to be the issue here, we're only interested in the address lines that the ULA can manage. And of course, we did see already that we had issues with one of the lines on all the lower RAM chips. So let's see whether that's also the case on the ULA side. Maybe it's a broken trace or something else. Just we need to verify before we do something. Let's start with the clock. It's pin 32. We start from the top, so this is the pin 40. The way it's nice to have some support, because like when you have shaky hands like I do, it's good to just make sure that you don't short anything and just that you have proper support to touch the pins with the oscilloscope probe. Okay, looking for pin 32, it's 40, 39, 38, 37, 36, 35, 34, 33, 32. This is the clock. 3.57, nice clock signal. Nothing wrong with that. You can save it, by the way. Okay, now let's continue. So we're looking for pin D0. It's the third from the bottom, pin 18 on the left side. This is it. So D0 seems to be fine. Okay, now let's go to D1. It's pin 21. That's convenient. It's just here. Again, what you can see is works pretty okay. Save it. After it's saved, we'll go to D2. All right, switch to D2. So it's the next pin. Again, there's some activity there. Save it. Next, we skip 2 pins and then land on D3, pin 25. Again, save it. Okay, we skip 1 pin and go to pin 27 on D4. Again, there's activity there, nothing wrong with that. Now we skip 1 pin again and go to pin D5, pin 29, which is the D5 data line. Save it. Okay, next pin is D6. Again, some activity. And then pin D7, the last data pin, again looking fine. All right, so we covered the data pins of the ULA. Okay, so let's get through the address lines now. As we can see, we have the lower bits of the address bus of the computer here on the left of the chip, starting with pin 5, ending in pin 11. We also have some additional two high pins of the memory. I don't remember exactly what it helps to address. I don't really think those would be an issue in our case, but we'll check them anyway. All right, let's start with A0. So address line 0, it's pin 5, so it's 1, 2, 3, 4, and 5. Whoop. Okay, address line 0 is actually not working correctly. We see the same pattern as we saw on the address line on the RAM, which is actually interesting because we don't really see the same thing happening on the memory. So address line 0 on the 4116 is pin 5. So it's 1, 2, 3, 4, and 5. This one is operating correctly, so the ULA is not really translated well. Okay, address line 1, which is pin 6. Let's see it. 2, 3, 4, 5, 6. This one is okay. Okay, address line 2. It's pin 7. Again, okay. Address line 3. Again, good activity. Next is address line 4, which is pin 9. Again, we see good activity here. Then we see the next line is address line 5 on pin 10. Again, some good activity here. And next is address line 6, which is pin 11. Again, some moderately healthy activity on that pin. All right. So it seems that we have one faulty line on the ULA, which is A0, which is actually not corresponding to the same address line according to the description of the 4116, so they are actually the opposite. Now we're looking for A14, which is pin 36. So it's 40, 39, 38, 37, 36. Should be here. Okay, again we see this pattern of the higher order bits of not changing so much because they're only operating when you change the big scope of addresses, so the code executing within one memory location or doing something in one memory location won't affect it. Right, and A15, which is pin 37, again similar behavior. Okay, and just to verify again, the messy pin on the 4116 is not pin 5, 1, 2, 3, 4, 5, but pin 7, which is A1 according to the spec that we have. We'll check that still. Let's switch the computer off and unplug, and then we'll continue with some summary of what we found so far. So after looking at what we did with the measurements, where does it leave us? The scope measurement is clearly showing that the A0/A1 address lines are corrupted. Well, the naming convention can vary. There is some multiplexing going on, so I wouldn't point to the fact that they're not reversed. However, we do see that there is a degraded signal on the address line only on the ULA side. So this points us specifically to the ULA being the driver of the issue, especially as we see the code execution happening normally. So that's confident enough for us to make a diagnosis, and confident enough or reasonably confident means that the evidence is pointing into one specific direction. I won't even mention the temperature at which the ULA is running because I didn't measure it correctly, but it's hot to touch. Mind you, it is pretty normal, meaning the ULA was designed in a way where only around half of its logic gates should be used when designing the logic within that chip. That's the Ferranti, the producer of ULA, expected. However, Sinclair engineers went a little bit farther, so around 60 or 70% of the gates are used, therefore they're overheating. However, this might not be the culprit, meaning like overheating or something like this is probably not the reason, or it could be the reason for the chip breaking, but right now, since it's broken, we know that's not the case. So basically, I don't see any alternative explanation that fits better. Now we need a proof, and the proof in this case would be to replace the ULA and see if the symptoms do disappear and if the machine is running correctly. So having enough to proceed, let's check. Now the obvious option to replace our ULA would be to use another one from a donor machine or some old stock or anywhere where we could find one. I did check. I don't see many circulating on eBay nor on the kind of Polish sites that sell those and so on. Sometimes those are some strange clones and stuff like this. It's not really recommended to use those at this moment. And another thing is you don't really know what you can expect from a chip like that. So the history can be pretty strange, might have been working in a very hot situation, let's say, so you might get some years out of that chip, you might get some months. It's kind of hard to say in reality. But while looking for that, I found a better option. It comes from pretty far away from here where I'm sitting right now. It has been produced in New Zealand, so it's the upside down, I would say, from our perspective. However, the chip is called the VLA82S Plus. You might have seen it sitting on the desk where we were doing the measurements. So here's the device itself. It also has a connector, that's the Plus version, where we have an extension providing digital signal output and also an audio output, since it emulates the AOI sound chip from the farther ZX Spectrums, the 128 lines. So it's a drop-in replacement for this 48K ULA socket. So we can just take out the old ULA and insert this one. It's an FPGA Xilinx chip. So it's a programmable array as well, and it emulates the hardware, and all is happening on the hardware level basically. So it's like a real ULA. It shouldn't develop the same issues on the address lines as we saw, and of course it has its own software running, meaning like the gate schematic can be altered in this chip using a programmer eventually if you would have some issues. Now, what it does, as I said before, is the direct RGB video output and also AI sound chip. And the RGB output is pretty important given that the original Spectrum and the quality of the output of the video wasn't that great. So having RGB will make our life less miserable, I would say. And I would say it's a meaningful improvement in that category. All right, so let's install it and see. So first we'll just install the VLA and measure the levels once it's there. And we'll see whether it actually did improve something or not, but I'm not really yet interested in the video output, let's start with measuring whether it's actually improving our situation. But first things first, whenever you're doing stuff like this, unplug the power just to be sure. It was disabled, but you never know. Now, getting rid of the ULA might be a bit annoying because it's pretty well mounted into its socket. So first of all, I'm using a plastic tool to just pry it a little bit on one side and another, but be very careful. I know we believe this chip is damaged, but maybe we can use it still somehow. I'll be prying it on one side and another, just to make sure that we're not really bending any pins. Right? We're getting close. Right, one side is out, the other is out. By the way, Ferranti ULA 6C001E-684, week 7. Okay, now that we're done, we knew, by the way, I don't know why this socket is mounted upside down, but if you could see during our testing, the pin 1 marker on the chip was here, up here. Now, the socket also has like a pin 1 marker, but here it's actually on the downside, so it's very, very annoying. It's not correct, so I made a little gray or silver dot just to make sure. On the replacement, we also have the pin 1 marker here. And now let's delicately install it. It should be better because this chip has proper pins. We'll push it in, not the whole, not completely though. Because I might still need to remove it for a second. But anyway, now that we have it, let's plug the power back in. And then let's do some testing. Okay, first of all, let's check the VCC1 and VCC2 voltages, but we have to be extra careful here, to be honest, just to not short anything. I wouldn't like to lose this chip. But let's see. Let's take some ground, and then let's check VCC, I think it's 2, pin 14. I'll verify it later. But long story short, it's 20, 19, 18, 17, 16, 14, 13. No, wait. 20, 19, 18, 17, 16, 15, and 14. So chip 14, the pin 14 is here. Let's check it. Oops. No. No. There's nothing here because the computer is not enabled. All right. Let's check again. 20, 19, 18, 17, 16, 15, 14. Okay, got plus 5 volt. And then we'll be very super sneaky and we'll try to get to the other pin. Okay, we know the computer is running again, by the way, because we're hearing the audio. Oh, come on. That's don't do that at home, please, because you might break stuff, as I will do it in a second. Okay, let me get the ground from here. Be more convenient, and then let me go with the pin underneath. That's why I didn't put it completely into the socket, because I want to get too close to it. It's plus 5 volts again. Okay, that's interesting. That was so it was an issue then. It was. So the ULA was taking so much power that actually had a drop on one of the voltage pins that we didn't see here with the new ULA. Okay, interesting. Now let's measure with the oscilloscope and see whether the the address lines are fixed. So let me switch to that. All right, well, back here with the oscilloscope. Now, what we're interested in are the data lines, starting with A0, which was our culprit here. So it was pin 5. Let's see what pin 5 is right now. It's 1, 2, 3, 4, and 5. Ah, we have activity. Save it as well. Okay, now A1. Again, nice activity. Nothing to worry about. And again, the machine is running. We'll also check A2, but I won't go, and A3, and I won't go deeper into that because it seems that we are having proper data signals here, so I wouldn't worry that much about it. And another one is here. It's fine. All right. And out of curiosity, let me check the signals on the address lines of the memory. So pin 7 was A1, pin 5, so it's 8, 7, 6, pin 5 looks fine, pin 7 looks fine. So the problem is fixed. Now let's see whether the video is fixed. So let me switch the computer off for a second. We'll remove the probe completely. Let's take a look at the screen and connect it. Once we verify, now it's the time to... It's perfect. Take a look. Wonderful. All right. Now we're testing the lower memory. Going through some patterns in the memory, as expected in the retroleum, pushing stuff into RAM and reading it. Where will we be? Hey, lower 16K of RAM is okay. But as you can see, the quality of the video is so-and-so, especially on the LCD screen where it's pretty visible. But now let's do the second trick of the VLA 82S Plus. In the meantime, the memory is being verified again. But let's do another trick. Upper RAM is okay. Everything is fine. Okay, let's switch it off. Here as well. And what we'll have to do is we need to connect this little funny connector to the ULA itself. Actually, it's going to be easier if I will pry it out. So, and do it before installing the chip. Let's not break it. We won't want to break it, so let's try to be delicate. Okay, it's not really... Yes, it's fully seated on this side and then it's completely unseated on the other. So let's do this side and then this side, and do always use some leverage because you don't want to excessive force operating on those things. All right, we're done. Nothing bent. Now let's connect this fine connector here. All right, so let's just make sure it's fully seated. Oops, now the pins are bent, but we'll fix that in a second. Nothing wrong. I hope it's the last time they will have to be in and out. It's me being clumsy. Okay, I think it's good enough. Now let's install it again. But now we'll seat it fully in the board. So there is sure contact. Now what you do with this fine extension is you actually install it over the change connector on the board. We'll do some proper cable management later. But now what we have, let's just check if it's still working. Okay. We'll just use our ears to verify whether all is okay or not. Okay, we heard the sound. All should be fine. Now let me look for a cable matching the output of this port. Here's the cable. I will show it in a moment. We can get rid of the meter because we won't be needing it right now, and it's in the way. So the cable that we're using is how many pins it has? 2, 4, 6, 7, 8. It's an 8-pin thing. It's compatible with the 128, some of the 128 variants. It's like, I think, +2 or something like this. And then it ends with the pin, we call it here the Euro socket. It's the SCART connection. So let's plug it into the machine with this little marked thing up. And then we need, I'll do the screen connection offline because I need to go behind the screen to do that. Now with that connected, we should be getting a nice video out of the new ULA that we just installed. Let's see if that is really the case. Sorry about the mess. I needed to move the monitor. Let's see. Let's start the machine. You can see the image quality is perfect, at least for me. It's a little bit blurry, but again, we're using an LCD monitor for this. It won't be perfect, but as you can see, the test is going. And we have the sound coming from the TV, not from the machine itself. All right, having done that, we need to put the machine back together. So let's do just that. All right, what I did so far is I did off screen put some electrical tape here to make sure that these wires that go between the VLA82S Plus and its video output box are not squeezed somewhere around the case, nor here, which already happened, by the way. The yellow wire here got flattened a little bit when the case was screwed together here. But long story short, I did that. The electrical tape, it's just regular black electrical tape, and it's not conductive, so it won't matter. And the 74LS chips are not running hot, so the tape shouldn't affect the thermals here. Now that we did the cable management, we need to put the rest of the case on. And in order to do that, we also need to delicately connect the keyboard membrane. Be very, very gentle with it. It's very fragile. And I think you have limited number of times in which you could do it. Okay, we have one cable connected, and here's the other. Okay, now they're in. You see they're almost, you can't see that, but they are almost stretched to the limit once the case is on. So we need to be super gentle with putting the rest of the case on. Let's get rid of this dust cover. Okay, no, we're not on properly yet. Okay, now I think we're good. Now we're good. All right. Okay, hold it together, turn it upside down. I'm leaving the ROM cartridge in just to make sure to verify it. So now we have a couple of screws that we need to put in. There is one that is of different length than the others. This goes here to the middle of the top of the case. Put this in first. I'm not tightening it completely. And now we'll do this. Put the screws in. And then again, when you're doing it, these are self-tappers, so you need to go counterclockwise until it clicks and then only screw it in. Otherwise, you're getting a new set of threads into the plastic and that won't last you long. So again, now it clicked, and then it goes nicely in. Let's do another one on this side. I'm not putting all of them in, but I'm just doing the opposite parts so that the case is secured. Now we're good. I'm not really screwing those in fully. We'll put all of them in. Okay. Another one on this side. I think I'm missing one. Yes, I think so. So let's see. We'll make sure that we're covered on the most crucial parts. So, okay. No, we're actually good. We have all of them. Yes. And the last one. Once we're done with all of them, we can tighten them. All right, let's start with the last one. So let's tighten the screw. Make sure not to rip the head of the screw as well. That's why I'm not exerting too much force on it. I'm doing just like a short runs, short movements. Okay. And the last one. Or almost last one. Good, and this is the final screw. Very good. Here's the machine put together completely. Now let's verify if it still works and that the keyboard is working as well. Let's connect the power and the video. I don't want to put too much force into it, but it's very tight. Okay, now we're good. Once we did that, I think we can use those legs just to make sure that we're not really touching the table here. Okay, we're done. Let's switch it on. It is running. We'll let the memory test pass once more, just to verify. You can see all the patterns. Once we're done, I'm really interested in the keyboard test because the keyboard might be affected by the connector from the membrane and not sticking properly in the mainboard and so on. So just to make sure, let's test it first. Okay, these are the upper memory tests running right now. They're done. Okay, let's get to the menu. And then we should have keys and capstone tests. So let's test the keys. And let's go 1 by 1, 6, 7, 8, 9, 0. Okay, the brake is actually braking. Now, where T, U, I, O, P works. A, S, D, F, G, H, J, K, L, enter, Z, X, C, V, B, N, M. We have cap shift. And then what else can we test? Cap shift and symbol shift. Yes. Okay, and caps plus space. Where is the space here? Okay. Now we're done. The machine is fixed and it's a full success. Now, one last thing that we would like to do is to go against what Sir Clive Sinclair intended for those machines. He wanted them to be rather educational than play. But of course, let's test it with some game. But I have to be very careful getting this external ROM thing out. And what we plug in is the Just Nano SD from Zaxxon. What it has is it has the Kempstone joystick port, which allows us to use our nice joystick, and then an SD card slot where all the software lives. So let's plug it in. And the nice thing about this thing is it's stable, it doesn't wobble, which is also quite good. It runs the ESX DOS, if I'm not mistaken. So let's run the machine. Okay. We should get into a file browser, if I'm not mistaken, when we press the button. Now that we do, we can go to a folder called game. We get to M. There is a game called Manic M-1. I wonder what that could be. No, we don't want training. Ow! God damn it. Let's wrap it up then. What we had in the beginning was a garbled display on a ZX Spectrum. We diagnosed it down to a single address line on the machine and a degraded power pin as well, the 3.65 volt VCC. What we resolved it with was a modern drop-in, which added RGB output and AY sound capability to the machine, so it extended its functionality and also future-proofed it a little bit. There was no soldering needed, and the diagnostic process, which was crucial in this case, took a couple of hours, and most of those hours were careful measurements. Nothing dramatic, but you had to go through every pin. But the broader point here is the process itself. So you needed the scope to check every pin on every data line and on every address line. One line was off, we saw it immediately. It was a bit marginal, there was still some activity there, so you had to be careful to look at the levels of it to understand the issue. But those kind of issues are pretty hard to find just using intuition, just replacing things left and right. So originally, if you wanted to fix this machine, you probably would have just started with the RAM replacement as what the online sources suggest and so on. By carefully diagnosing it, I learned a lot. I knew nothing about ZX Spectrum before I had this one and had to diagnose it. I did not use Z80 anywhere in my career, let's say. Maybe not a career, but in my history. And I never actually understood how the Spectrum works until working on this one. So I learned a lot about the ULA, the uncommitted logic array chip from Ferranti. It's a very fascinating story. I really recommend to read about this, how this was created and how it helped Sinclair to get the machine on the market. Now, the replacement of ULA 82S Plus is also worth knowing about. Even if your Spectrum is working perfectly, if you want to have RGB outputs, or if you want just to future-proof the machine, it's a nice solution. It's not really something you would do on a completely working machine, but if you want to kind of improve it, then that's a nice enhancement of it. So that's about it. Let's wrap it up. Next up, we'll have, I think, an Amiga 1200 with no video output, another one in my collection. I started working on this, but it's not finished yet, so we'll be doing that one live compared to this machine, which was kind of retrospectively analyzed after the fix was already done. If you liked the process of the fix or the video itself, please give it a thumbs up. Please subscribe to the channel. I will be adding some more content about fixing my huge amount of machines that I have and I collected over the years. I really like working on those that are faulty for some reasons, because then I can learn quite a lot about those, and I hope you will be able to learn about it too. I really hope for your comments down below. If you see that I'm making a lot of mistakes, please highlight those and let's see what we can share with the community as well, knowledge-wise. I am not a professional. I'm not really busy with electronics. All of this I'm learning as we go, so bear that in mind. Thank you very much and see you in the next video.